So in this video, we're going to build on what we've already learned about superposition of two waves, and we're going to look at the phenomenon of interference. So to start with, we're going to consider what happens if we have two identical sources of waves in a medium, but these two sources are a fixed distance apart from one another. What pattern of waves is going to result? So here we have two identical sources of waves. So this is one source, this is the other source, that are emitting waves. And what I want to know is what happens at this point here at an angle theta from the line joining the two sources at a distance r away. Now, the waves from this source are going to have traveled a distance r1, and the waves from the other source are going to have traveled a distance r2 here. So there is going to be a phase difference between them because r1 is not equal to r2. So the question is now is how does the phase of a wave change with displacement? Well, if you remember, we defined the wave number here, k, and this was the rate of change of phase with respect to distance, right? Remember, we had this in radians per meter. So this wave number multiplied by the distance, or the difference in the distance, will give us the change in phase, right? So the rate of change of phase of a wave is just k times the displacement. And if you look at this, right, if we had a difference in these distances here, if delta r was equal to one wavelength, then that would mean that after we've traveled this distance, we'd gone through a phase difference of 2 pi, right? So this corresponds to one cycle by definition, right? So if we take k and we multiply it by lambda, right, this gives us 2 pi over lambda times lambda equals 2 pi. So just as a quick check to see whether this makes sense, we've seen that it does, because if you have a length difference of one wavelength, you expect the phase difference there to be 2 pi, and that's exactly what we get. So to calculate the phase difference, all we need to do is multiply the difference in the propagation lengths multiplied by the wave number. So what we want here is our phase difference when we're adding these waves together at this point is going to be k times r1 minus r2. Now, if we take this point and we make it a long, long way away, then r1 is going to be roughly parallel to r2. Right? Now, obviously, they're not exactly parallel because they do meet at this point, but if this is an incredibly long way away, then it's going to turn out that these are roughly parallel, and we get what will turn out to be a very good approximation. So we're going to make this assumption that we are in a long way from these two sources, and we can make the approximation that these two lines here are roughly parallel to one another. So let's zoom in on the sources and have a look at these in detail. So here we are zoomed in, and so this is the line R1 and this is the line R2, and I've drawn them here so that we're assuming that they're parallel, and we're adding them together way off here, way off the screen. So if I make this assumption and I say that the distance between the two sources here is d, then if I draw a line along the midpoint here, then if I draw the perpendiculars from that line to each of these sources, which each have equal amplitude a, then this distance here is the difference in the propagation lengths, right? Because the waves from this source propagate out along here, the waves from this source propagate out along here, and so if I carried this line on down to here, this would be the extra distance that they propagate from the second source here. So if I look at this right angle triangle, this length here is delta r over 2. And so what I'm going to just do is use simple trigonometry. The sine of theta, so theta here is the angle that this line makes to the perpendicular, which means it's also this angle here by geometry. So the sine of theta is the opposite, which is delta r over 2 divided by the hypotenuse, and the hypotenuse, since this is the right angle here, is just d over 2. So the halves are going to cancel, and if I take the d up to this side, I get that the difference in propagation length is just the separation of the sources multiplied by the sine of theta. And so the phase difference here is just the wave number multiplied by the difference in the propagation length, because remember, these things are perfectly in phase and they have the same amplitude. And so my phase difference between these two sources at my point, which is a distance r away at an angle theta, is going to be k times d times sine theta. So what I want now is I want my phase difference I want to calculate where I'm going to have maximum constructive interference, and so that is when my phase difference here is going to be equal to 2 times n times pi. So in other words, I could have a phase difference of 0, I could have a phase difference of 2 pi, 4 pi, 6 pi, any even multiple of pi. So that must be equal to kd sine theta, and that means that I'm going to have this maximum when sine theta is equal to 2n pi over k times d. So I'm going to have multiple angles where this is going to be satisfied, because I'm going to have n equals 0, 1, 2, 3, and so on. Now this is for constructive interference. Right, so this is constructive interference, and I'm going to have a maximum. Now for cancellation, I want an odd number of pi, and so that means that I want my phase difference here to be 2n plus 1 times pi, and so that is going to give me a condition on sine theta of it being equal to 2n plus 1 times pi over kd. So I'm also going to have angles for theta, multiple angles, because of course n here is equal to 0, 1, and so on. I'm going to have multiple angles where I get perfect cancellation. So the pattern that we expect to see from this is certain areas where I'm going to get constructive interference, so I'm going to get large amplitude, and other areas where I get perfect cancellation. So here is the pattern that I get when I add these two wave sources. So this is the source here, and I've added the waves that are produced by these two sources. And obviously when I'm close to the sources, I don't get exactly what I'm expecting, because remember, we made this approximation, so it's only valid, our calculations are valid when the distance from the sources is large. So it's not going to work close to the sources. But what you can clearly see here is that there are lines where you get cancellation. And these lines come roughly from the center. Now, obviously, as you get near to the center, they deviate, and that's because our approximation is not valid. But as you get long distance away from the center, you get these fixed angles. So this is the center here, and you can see that they roughly converge at the center. So this is where you get cancellation at fixed values of theta. So cancellation at fixed. Similarly, you get constructive interference along these lines. So here you're going to get constructive interference. And the thing to note here is that one of these lines for constructive interference, so this is where you get the large amplitude, you get them in phase. And one of these occurs when theta is equal to 0. And that was also one of the predictions we had. Remember, we had it that sine theta here was going to be equal to 2n pi over k times d, and one of the values for n was going to be 0, and so that would mean that theta is equal to 0 is one of the solutions when n is equal to 0. And again, that's borne out. So our prediction matches this calculation here. So let's see if that's actually what happens in real life when we add two sources together. So we've just seen the maths behind how two identical wave sources can create a pattern in 2 dimensions from the interference of waves. So what we're going to do here is we're going to actually demonstrate that. This device is called a ripple tank. It consists of a small amount of water on the top of the device, and in poking into it we have a little prong, and that prong vibrates to create waves on the surface of the water, and you can see there's a light shining through the water and focusing an image onto the screen of those waves. Now, normally the waves on the surface of water would travel too fast for you to be able to see what they're doing. So here what we've done is we have a shutter underneath this which flashes the light, so the light isn't shining uniformly, it flashes several times a second, and that slows down the waves. You essentially see the waves only a few times a second, and so the waves appear to move only slowly. In fact, what you're seeing is you're seeing several wave fronts later projected onto the screen, and the cumulative effect of that is that it appears that they've only moved very slowly. So what we're going to do here is show you first of all what it looks like for a single source. So you can see the circular wavefront moving out, and that's what we've got set up here. And then we'll show you the same device, but with a two-pronged source, so that will generate two identical sources of waves, and we'll see the interference pattern that results from that. So here we have the ripple tank set up now with the two-prong vibrator, and it's creating two identical wave sources that are also perfectly in phase because the whole prong is going up and down together and hitting the water at two locations. And if you look closely at the pattern, you can see the pattern agrees exactly with what we predicted from the maths that we used. There are these lines coming out from the two sources where there is a destructive interference of waves. In other words, along that line, the two waves, one from each source, add together out of phase and generate perfect cancellation. In between, you end up with the two waves adding together in phase, and so you get twice the amplitude that you get for a normal wave if there'd only been a single source. So, as the ripple tank has shown, in 2 dimensions, our predictions agree exactly with reality. Of course, in between the two sources, the pattern is complex and it doesn't follow the distant field approach. So we've seen the interference pattern that we get now from two identical wave sources, and it doesn't matter whether those are ripples on the surface of water or they're sound waves traveling through air, we get the same pattern. But this is the pattern that comes from two identical wave sources. What happens if the two sources are not exactly identical? And suppose we have two sources, one with a frequency omega and the other with a frequency that's slightly different from omega. So we have two sources with slightly differing frequencies. So our wave function now is going to be the sum of two waves, and we're ignoring the position dependence because we're fixing our position. We're only listening or seeing the waves at one point in space. And so what we're going to have is we're going to have a wave e to the I omega 1 times t, and we're going to add to that the wave e to the I omega 2 times t, and we've got this additional factor a in here where this is the amplitude, and we're assuming that we've got equal amplitudes for the two sources, but that we have different frequencies omega 1 and omega 2. So to add these together, I'm going to take out a factor which will look a little bit funny, but we'll see where we go. So I'm taking out a factor of a because we've got a common amplitude, and then e to the I a half omega 1 times t. So if I do that and I take it out of this, well, I'm going to be left with a factor of e to the half I omega 1 times t for this term. So I'm going to have e to the half omega 1 times t here. And then here I'm going to be taking it out, so I'm going to have a negative factor. I'm going to have 1 over this, which is just e to the negative power. So this is going to be plus e to the minus I a half omega 1 t times e to the I omega 2 t. So now I'm going to take out a factor of e to the half omega 2 times t. So this is going to give me an expression that looks like this. So I have my I a half omega 1 times t times e to the I a half omega 2 times t. And now in here, well, because I'm taking it out of this term, I'm essentially multiplying by e to the minus a half omega 2 times t. So here I'm going to be left with e to the I a half omega 1 t times e to the minus I a half omega 2 t. And then this term here is going to be plus, well, when I multiply it through by minus a half I omega 2t, I'm just going to make this a half. So this is going to be plus e to the minus I a half omega 1 times t, e to the I a half omega 2 times t. Okay, so now what happens? Well, when I multiply two exponentials together, I just add the powers. So I can rewrite this now as a times e to the I a half omega 1 plus omega 2 times t. And now in these brackets I can write this as e to the I a half, and now I've got omega 1 minus omega 2 times t, plus, and then here I've got minus omega 1 and plus omega 2, so I can write this in the following way, e to the minus I a half, and now omega 1 minus omega 2 times t. Okay, so to go further, we need a little identity. And so what we're going to look at now, just to simplify things, is e to the I theta plus e to the minus I theta. Now, I can write this out using our trig functions, and so what I get is cos theta plus I sine theta, so that's e to the I theta, and then here I've just got e to the minus theta. Well, cosine of minus theta is just cosine theta, so I'm going to have cosine of theta here, and sine of minus theta is minus sine theta, so I'm going to have minus I sine theta here. So if I look at this expression, the sine thetas cancel out, and I'm just left with 2 cosine theta. Now compare that to this expression here. Well, if I set theta to be a half of omega 1 minus omega 2 times t, then by adding these two terms together, I'm just going to get 2 times the cosine of a half omega 1 minus omega 2 times t. So what does that leave me? Well, that leaves me with psi of t, our combined wave function. Well, I get a factor of 2 from this, so it's going to be 2 times a. And I'm going to drop the implied real notation now. So this, the real part of this, is just cosine of this. So this is going to be cosine of omega 1 plus omega 2 over 2 times t. And then here, of course, I actually get cosine. So this is going to be cosine of omega 1 minus omega 2 over 2 times t. And so this is now my combined wave function for the sum of these two sources with slightly different frequencies, omega 1 and omega 2. So next we want to have some idea of what this is actually going to look like. So here's our expression which comes from the sum of these two different wave frequencies. So let's have a look at this. Well, let's remember a few things first. We can write the average frequency, or average angular frequency, omega bar, as a half of omega 1 plus omega 2, right? Because we add the two things together and then we divide them by 2, since we've got two items, and so this gives us the average. So this is the average of the average frequency of the two sources. So this is going to be, we can write this as the cosine of omega bar times t. So this is going to oscillate with the average frequency of the two sources. Now we can also write down the difference of the two sources, the difference in frequency between the two sources, as omega 1 minus omega 2, and so this is the difference. And so here we can write this as cosine of a half delta omega times t. And so this is a half the difference in frequency. So this is going to oscillate with the difference in frequency. So what's that going to look like? Well, supposing we take the case where we have two sources where omega 1 is roughly equal to omega 2, but not exactly equal, right? So omega 1 is not equal to omega 2, but they're comparable in size. So say, for example, we have 1 kilohertz here and 1002 hertz here. These would be roughly equal, but not exactly equal. Now, in that case, what we're going to have is that the average of those two frequencies is going to be comparable to the individual frequencies that make it up. right? So if we took here, if we said that this was 1,000 and this was 1,002, then this would give us 1,001, right? Which is comparable to the individual frequencies here. But the difference in frequency is going to be a lot smaller. So in this case, we're going to get a lower value. And so in this case, it would be, if we use these examples here, where we have 1,002 and 1,000 for the two angular frequencies, then this would give us, 2, right? So, if, a small difference. So what's that going to mean? Well, it means that this is going to give us a very high frequency oscillation, right? So we're going to get something that has a very high frequency. This term, on the other hand, will give us something that has a very low frequency of oscillation and a very long wavelength, if you like. So we've got a low frequency and a high frequency. So what's going to happen is that these two terms here, which vary slowly, I mean this is constant so it doesn't actually vary at all, are going to give us an effective amplitude. And this effective amplitude is going to be multiplied by this high frequency wave here, and so we're going to get a high frequency wave which varies slowly in amplitude. So let's plot it and see exactly what that looks like. So here we have what it looks like for two different examples. So this part of our wave function here, the difference, this is the low frequency part that gives us this envelope that you can see here is the black dashed line. So this is our low frequency part that gives us this black dashed envelope. This is the high frequency part that gives us the blue line that is oscillating up and down very rapidly. And as you can see, what we observe is that the amplitude of this high frequency blue wave oscillates. It's got a high amplitude here, low amplitude, high amplitude, low amplitude. Now notice that this we can write as the cosine of a half delta omega times t. So of course what that means is if I overlay this, it's one wavelength of this looks like what I'm drawing here. So it goes up, down, and back again. However, what we hear, if we're listening to it, if this was a sound wave, is we would hear this high frequency signal, and we would hear the change in the amplitude, or if it was light, we'd observe that the light would get dim and bright again. So what we're seeing is, in terms of the amplitude, is one of these things from peak to peak. But notice, even when it's large and negative here, because it's been multiplied by this oscillating signal, it doesn't make any difference. We don't see any difference between what we observe here and what we observe here, even though this amplitude has flipped in sign. So what that means is that the frequency of these loud, if you like, if it's sound waves, or bright if it's light, whatever adjective is appropriate for the wave, these periods of large amplitude, the frequency of these is going to be just delta omega. So the omega of the beats is going to be equal to delta omega, and I'm actually going to put a modulus around it, because if omega 2 is bigger than omega 1, then the fact that this is negative doesn't matter. All it would mean is you'd be going down here first and then up here, but again, since we're multiplying it by this oscillating signal, the sign of this cosine term doesn't matter. It's irrelevant. What matters is the magnitude of this cosine term, right? The modulus of the cosine term. So this beat frequency is going to be given by this term here. So this is the angular beat frequency. So it's not going to come as a surprise that the beat frequency itself, since this is just a 2 pi factor in here, and we're going to have a 2 pi factor in here, and we can cancel those 2 pi's, is just going to be the modulus of the difference in the frequency of the two sources. And this is called the beat frequency. And it appears as a change in the amplitude of the wave. So let's have a look at that for some real waves. So now we've seen that if we have two sources with slightly different frequencies interfering, we should get this amplitude modulation where the wave has a frequency that's the average of the two frequencies you're adding together, and the amplitude modulates at a frequency that is half the difference between those two different wave source frequencies. So what we've got here to demonstrate that are two identical tuning forks. But on one of these tuning forks we've added a small weight, and that makes it vibrate off frequency. So we have two similar sound source frequencies. There's not a huge gap between them, but there is a small frequency difference. And we have here a microphone that is attached to the oscilloscope, and as usual our wireless microphone is causing interference problems, so I'll have to turn that off when we do this experiment. But once we've seen it on the scope, I'll then turn off the oscilloscope, put the wireless microphone back on, and you can listen to the beat pattern. So at the moment what we've got it set up with is we've got it set up with quite a large difference between the two frequencies, so that the difference between the frequencies will give us an amplitude modulation that's comparable to the frequencies themselves, and so you can actually see the waveform on the oscilloscope. So what you should look for on the scope is this envelope where the wave increases in amplitude, decreases, increases again on the scope. So, but you won't be able to see it until I turn off my wireless microphone and hit the two tuning forks. So here goes. So what you saw there was the beat pattern. Now what we're going to try is we're going to use this wireless microphone to try and pick up the beats as well. So initially we'll try it with this large frequency difference, and you might not be able to hear it. Then I'll lower this weight down here, the frequency difference will get smaller, and the beats should become more noticeable as a constant tone that's increasing and decreasing in volume. So you probably couldn't hear much of the beats there, but let's try it with the weight lowered so the frequency difference is less. And you now should have been able to hear a clear change in the volume of that tone. And if I move this weight up a little bit, the frequency will increase. So the tone, the rate at which the tone changes volume will increase in speed. And if I put it down to its very lowest point down here, you should get a very low increase, a very low rate of change of volume. In fact, that's such a low rate, I'm not sure you could actually hear it. So there we have the phenomenon of beats. Now, what we've shown is many different interference effects with waves, but there's one remaining effect that we need to discuss, and we'll do that in the following video, and that is the phenomenon of standing waves.